But then I had also requested you from the Higgs to Tau data set if you can play around, produce some ROC curves, try to do some optimization of the model and see how much better you can do. I believe I got 2 or 3 replies. I think Riteshda sent me one and someone directly mailed you. But I'll be happy if more of you can do some of those exercises, which was, let's say, beyond the quiz. But unless you actually play around, given now you have a data set, you have code, that's when you will really learn. Number two, today there will not be a coding exercise, but there will be derivation exercises. I will list them during the lecture and I will send an email to the common thread explicitly specifying what the derivation is. And I expect, okay, I mean, those of you who want to do it to send it back to me as a PDF only. Of course, on Wednesday, once all the concepts, the theoretical concepts are covered, then there will be a coding exercise and there will be one more data set I will pass on to Riteshda so that he can download and share with all of you. Okay, so with that, let's get going. First, I want to do a quick recap. So we had sort of laid the groundwork for machine learning, wherein we said that the basic goal is that you have some input data, which is characterized by, let's say, uh, n input features for each of them. And you might have m data points. I might use these interchangeably. And then you have some model. I'm using different notations, but you see that from the context it will make sense. And then from here, you have a prediction. Okay. The prediction, but this is the only thing that is specific to this kind of a formalism is that it is supervised learning. Uh, why so? Because not only do you have n input features, you also have a label to the data. That the entire data that I have some input features which is useful for the problem I'm working on, but each of them have a label. It can be a signal or a background, as in the data set I had shared with you, the Higgs-Tau data set from Atlas. It may be a continuous number. I have hits in a calorimeter. What is the energy of the particle that gave rise to those hits? In that case, it becomes a regression problem because the target is a continuous number. But regardless, I try to learn, train, fit a model which has theta number of parameters. So I split my data set, use a part of it to train. Once I train, this model is completely specified. Then when I have unknown data, data that was not given to it while you were training, but given that my model is completely trained, I put in those new data, it will give me a unique prediction. So this was the paradigm of supervised learning that we set up. And then in doing so, we said that the so now the problem becomes, how do we learn these thetas? So I have some objective which we call something related to a loss plus something what we call regularization. Okay, the loss will depend on m n theta. right? Because the model will predict something. Let's call that h theta x. I had used yi hat. All those things are similar. I know, but for each uh, I, let's say, ith point, the model will predict something, but I have the label for that point. Now, for all the points you're using for the training, you want to minimize this quantity, right? That's what we had done. We had MSE, logistic loss, mean absolute error, many things we had seen. But the regularization, as we saw in the BDT example, that does not depend on the number of points you are training on, number of input features you have. It doesn't care about all that. It only cares about the complexity of your model. So it only cares about the number of theta parameters, potentially in what form you're using them. Why? Because you want to penalize your model from becoming unnecessarily complex. Clear? So while the loss term you're minimizing over your entire training data set, the regularization term doesn't care how many points you have, all those. It's only to protect your model from becoming more complex. And a simple example is, for instance, chi-square by MDF. Chi-square by MDF has a denominator which is number of points minus number of model parameters. That is the analog of the regularization part. So if you have already found a certain number of model parameters, that gives you a chi-square by MDF of 1. By increasing the number of model parameters, you will violate the condition. It will start going much, much below 1 and you'll have overfitting. Okay. So given a model, this is your objective. Then, of course, how to minimize the objective, that depends on the kind of model, etc., that you're dealing with. And we dealt with two particular examples, SVM, BDT, but in particular, gradient boosted trees, GB or GBR, regression trees. Okay. So in SVM, we saw it was a very cute concept where you define your goal as given some data points, you define some concept called support vectors, and in particular you try to maximize the separation between the positive and the negative support vectors. We saw the entire math of that and we concluded that this was an example of what's called a quadratic optimization problem, because both in the prediction of an unknown point as well as in the Lagrange multiplier optimization, these x's, unknown x's, only appear as squares. It appears as a x dot x of different flavors. And then we saw that just because that happened, you could also deal with nonlinear problems using the concept of kernels, where you transform from one space to the other, but you don't need to know the exact transformation, but you need to know the dot product of the transformation. And the final thing, this is what I'm expecting to see in the exercise, is this concept, what I drew here right now, is what's called a hard max support vector machine, where in this no man's land, no point is allowed to be there. So then we define that you can relax this condition by defining an epsilon, where in the defining equations initially, you had an equal to 1 imposed. So let's maybe draw back. So right here, so in the governing equations of the support vector machine, you have this yi xi dot w plus b, the weights and biases, where it's greater than equal to 1 when it's hard margin, but you can allow for what's called slack, and then you are allowed to have points in no man's land. You're allowed to have points in no man's land by whatever margin you expect to have. And you will see if you try, and I showed you then in the class of the SVM in scikit-learn how to change the parameters and do it. And you will see if you have tried the example, that unless you allow for slack, you will get a very bad model in terms of that accuracy of the prediction. Also AUC, ROC comes. Okay. But we see that in SVM, there's a fundamental drawback, that you are defining the optimization problem, that is to maximize the separation between positive and negative support vectors, subject to a slack if you choose to have it or not. There is no way you can put in a custom loss function, say based on your understanding of your problem. There exists some loss function that makes the most sense to minimize. In an SVM, there is no way to impose that. Then when we came to the boosted decision tree, I've shared you the slides, so I'll just say it mostly verbally. So there, even though you were using decision boundaries to determine what is the optimal splitting of your input feature space, so that you end up with maximal number of positive or negative classes. In principle, you can do multi-classification as well. But here we introduce two concepts that we try to motivate why just using a decision tree is not optimal. And we introduce the concept of boosting, where every subsequent step of splitting the phase space into trees has a specific goal. The goal is to fix an error in the previous step. So we did some example. If I do it this way, suppose there's a minus, there's a plus. So if the first tree boundary I put in like that, then in the next step, my main goal will be to define a boundary to classify the minus correctly. Okay, this is too extreme that I took. Suppose like so. And this plus correctly. Okay. So how do you do that? You play with event weights. You can weight in the next step. You can increase the cost of getting that minus, this minus you have here wrong. Likewise, and then the final tree is a weighted combination of all the splits that you did. The next thing we sort of nearly derive step by step, the XGBoost way of doing things, where the trees are grown additively just by this concept that we discuss right now, wherein the problem is being reduced to what is the objective of adding the next tree, right? You have grown a tree of a certain depth with a certain number of leaves. So now I'm introducing a new split in the tree, a new depth, a new set of leaves. So we reduce the optimization problem to this ith step. Why? Because if I know what is my objective from the ith step, I can iterate from 0 to n steps to get the most optimal problem. And here we saw that we have full freedom to use any loss function that we want. And how did we do that? We took a Taylor expansion up to second order, right? So that's how we implemented an arbitrary loss function in the XGBoost way of doing things. But then that imposes a constraint on the loss function that it has to be differentiable up to second order. And then the math follows transparently. You can do gradient descent based on the loss function, and you can get the optimized set of trees. Okay, so this is then where we had stopped, and your task was to compare SVM, BDT, look at balancing the samples, get the ROC curve. I believe many of you have done that. But before I go to the agenda of today, I want to introduce just one thing, which maybe we'll take up an exercise in the main school, but this concept is general, so I just want to cover it. The concept is one of a semi-parametric regression. Okay. So let me specify the problem. Suppose I have a calorimeter. Again, just like before, at any point anything is not clear, please stop me there and then, because many of the concepts we will cover is based on some things that we will discuss now. Okay. So I am drawing a very specific kind of a calorimeter. It doesn't have to be this way. Okay. So I've just drawn some voxel kind of a structure. So suppose this is like a simplified calorimeter, which has some cells like that. Now an electron or a photon, whatever you please, some electromagnetic particle comes and hits in the calorimeter and deposits energy. So this irregular shape that I drew is what your clustering algorithm. So I have to cluster the hits to say, okay, these many hits in these many crystals belong to this electron or this photon or some other object. So first there's a clustering algorithm that will run, that will tell me, okay, in this event, you please pick these up. These belong to your electron. Okay. So then what I will do is my energy reconstructed energy of this electron is equal to sum over energy I element of cluster. Clear? This is something that you would do. So then how do I determine, do I need to correct this energy? Yes, you need to correct this energy. Why do you need to correct this energy? Well, in a real life, there is a finite gap between two crystals. Some of the crystals may be dead. The clustering algorithm may not be perfectly efficient. There might be a true deposit somewhere, which your clustering algorithm isn't picking up. There can be noise in each of the crystals so that the signal component that you're picking up is riding above the noise level, etc., etc. Okay, so I need to correct for this energy. And okay, let me just give a reference. You can Google, this is the reference, CMS EGM 17001. And there's a section on the regression for energy reconstruction. I'm just highlighting the salient features of that. Okay, so then, okay, by the way, is the formulation of the problem clear to everyone? I have
Yes, sir.
Okay, good. Okay. So now, how do I judge the quality of my reconstruction? So clearly I have to take the help from simulation. So I can simulate individual particles that are incident on the detector and run a jam for detector reconstruction. So then at sim level, at simulation level, I will have E reco electron. But because I've simulated it, I know what its true energy is. So I will also have E true electron. Okay. So now when I plot this quantity, I am calling this response or R of an electron. So when you plot, one sec, just give me one sec, sorry. How do I make it hide? Can I hide it? No. Wait, let's do it this way. When you plot RE, so for perfect, okay, now question to you. If my reconstruction was perfect, what would RE look like? Am I audible?
Constant.
Yes,
1.
sir.
No, not a constant. One is straight line is not a right answer. No. Look, RE, it's not versus energy. So someone said one, good, but what functional form? I'm not plotting RE, I'm histogramming RE. A delta function, right? A delta function at one. Why? Seem people are foxed. Oh, we agree it should be a delta for perfect in the real world. Not in the ideal world, not in the real world. It would be a delta function at one, correct? Is there a disagreement? Good. Now, in the real world, every calorimeter has a resolution. That is an intrinsic resolution of the calorimeter. No ML algorithm is allowed to beat that because physics demands a certain level of uncertainty in reconstructing the shower. So, in the real world, you will get something that I will come to. But before you apply any correction, you will see that you're okay. I drew it incorrectly. Let me draw it correctly. Just give me one second. There is no sort of guarantee that it would look like that, but I'm just saying in the real world, before you apply any ML correction, and don't take this point as zero, this don't take this point as zero, because of this. So you end up with a distribution whose peak is not at one and which has an asymmetric tail. Why is peak not at one? Because almost always your reconstruction is worse than gen. I would have lost energy upstream. I would have lost energy in the gaps. I would have lost energy outside the cluster. Right? So your E reco is lower in general than E true. So that's why first, before you apply any correction, your peak is below one. Number two is you have, so then the second question is why are the tails asymmetric? If I had an ideal calorimeter, in an ideal calorimeter, you have a Gaussian resolution, right? Stochastic, constant, all these terms. So I could still understand the peak was away from one, but it should have been a Gaussian. The reason is the response of a calorimeter itself is energy dependent. See, in this RE that I wrote, in this RE, I am not drawing RE in some narrow bins of energy. I'm saying what is the total cumulated RE, the response. So it's more likely that a higher energy electron is going to leak than a lower energy electron, right? So when you accumulate these things where there are sub distributions in the full distribution, you end up with asymmetries like this. Okay. So are we on the same page that in a real calorimeter, before you apply any ML correction, if I plot response number one, its peak will be lower than 1. Now, mind you, in some papers, they define response as E true by E reco. In that case, the entire argument flips. Your peak would be greater than 1, and then the tail on that side will become a tail on the other side. So be aware of that. Look at the distribution. Concept remains the same, but some people flip the definition. But for me, this is a much more natural definition than what people might use. Okay. Are we on the same page till now? Hello.
Yes.
Okay, good. So now you are designing a ML based regression. To correct this, what do I want? I want to what? Okay, how do I do a different color? This one. So I want to translate this peak as close to 1 as possible, and I would have wanted to go back to the delta function, but physics doesn't allow that. At least I want to go back as close to the intrinsic calorimeter resolution as possible, right? You know that sigma E over E has contribution from certain terms. This is addition and quadrature, B by E, quadrat C, right? So I want to go as close to ABC terms as possible. Okay. Uh, so then let's say I choose whatever model I want, DNN, BDT, fancier models, all that is fine. My question is, what loss function will you use? Right? In particular, when we saw that your response was asymmetric. What notation did I use? RE. Okay. So what is the first thing that, so far, what have I taught you? I've taught you that, well, if you want to, so this is a regression. So you will not use that logistic or the cross entropy loss formula that y log 1 minus y, not that stuff. You might use a mean square error or a mean absolute error, which is something like y for the ith point that's predicted by the model, and yi what the true data is. You can use this, you can use that. I also motivated you could use something like that maybe, right? Why? Because this has the dimensions of, if you use this has the dimensions of sigma E over E, something like that. Okay. But what's the most important point here? All these loss functional forms are symmetric, right? Whether I predict higher than the, sorry, there's a mosquito. Whether I predict higher than the true value or lower than the true value by the same amount, the penalization of the loss value is exactly the same. Okay, that's what this MSE, MAE are telling you. However, what you see here is that over here, due to leakage, your response is such that due to no fault of the electron, it is more likely to get under predicted than over predicted. Right? So suppose let's take this higher energy electron that we have. So this higher energy electron will of course have a genuine calorimeter introduced smearing, wherein it can the predicted value for a high energy electron can be on either side by these terms, right? Of course, there's an intrinsic energy dependence as well in those terms that has to be taken into account. But because I'm a high energy electron, I'm also more likely to leak, right? So over and above, over and above the Gaussian smearing, I have a loss that comes from leakage. If I were to choose a symmetric loss function, then this leakage bit, which is real, will be penalized much more than the overprediction, right? So in a symmetric loss function, different color, maybe blue. When you were to use a symmetric loss function, this tail that you have, which is due to a physical cause, leakage, you are penalizing. When you penalize that, it's like you don't learn from it. Just because I leak, I predict much lower than what the symmetric loss function wants. I try to sort of give less weight to those events. And when I do that, I'm unable to correct for it. So you will see that whenever you do a problem like this, a calorimeter, real calorimeter reconstruction with a regression, if the response is asymmetric, which almost always it is to different degrees, if you use a symmetric loss function, no matter how fancy you make your algorithm, it will never beat a simpler algorithm with a asymmetric loss function. And this gets more and more extreme as the response gets more and more asymmetric. Okay, so then where does this semi-parametric business come in? Is you redefine your problem. So what is the original problem? Please predict me back the true energy, right? That's what the original problem is. I give you some input features, maybe based on this hit pattern, sum of hits, some other features of hits. I'll give you some input features. Please tell me what my true energy is. In the semi-parametric way of doing things, you instead, okay, let's take this somewhere here maybe. Instead of directly predicting the target, predict the parameters of a probability distribution function that represents the target. Okay, so instead of directly predicting the energy, I can say that my predicted energy is distributed, let's say, like a double-sided crystal ball, right? So I try to predict the parameters of a double-sided crystal ball. But I know that the mean of the double-sided crystal ball is the energy. If my energy is distributed like a double-sided crystal ball, then what is my best estimate of what the energy is? It's the mean of it. But just by taking this approach, you can incorporate an arbitrary loss function, in particular those that are asymmetric. From its most probable value, you predict the energy, but now you get for free the resolution also. Original problem in a regression, please tell me what my energy is. Fine. But do I know what is how to what degree I know that this energy is the right energy? In the original regression, you don't. But the moment you predict the probability distribution function explicitly by which your target is distributed, the mean value is the energy, but you're also predicting the two Gaussian resolutions of the crystal ball, which is nothing but, oops, sorry, how do I do undo? Anyway, I'll do it later, which is nothing but these energy parameters. Okay, so that more or less specifies the sorry, the semi param regression. Of course, I think in the main school last time also we gave an exercise. This time we can also give an exercise. All of you who are interested, but conceptually it is algorithm independent. Not like it's not like it works for BGT, not for DNNs, but it is really designed for calorimetric reconstruction, where you have an asymmetric response, and number two, not only do you predict the true energy, but you get the resolution for free, which you can later use in different steps. Okay, I think I'll stop here. So I think I digressed slightly, but it's an important concept to cover. Are there any questions? Okay, good.
Sir,
Yes.
so if we're trying to predict the parameters of the PDF that is representing the target, how do we define a loss function for this then? Like I want to compare what the actual parameters are and what my predicted parameters are, right?
Exactly the same way. So when you are defining the MSE loss, you are assuming that the error or the residuals are distributed like a Gaussian or a standard normal distribution. So here you see that what is the crystal ball? RE, oops, sorry, which is E reco by E true, right? E reco in this case is nothing but E predicted. So if I say my E predicted by E true, which is nothing but the label of your input data, is distributed like a crystal ball. So then you can transform. So you know your y hat and yi from this equation, and you know that this is distributed as a double-sided crystal ball. You can transform it to the loss function, right? Just like over here in your MSE, what are you doing? You're saying your errors or your residuals are distributed as a Gaussian effectively, and you're minimizing that gap. So here you do exactly the same thing, except you have this constraint that your response is distributed as a crystal ball.
Okay, understood.
If you want to do it explicitly, then I recommend you do the exercise. But that's the basis, that your response is a crystal ball. You know your E predicted E2 to represent them in the response. So you like do the algebra to have a minimization equation in that term. Okay. So now Okay, so this is my agenda for today's class. In the next class, assuming we finish all these, we will look at some advanced topics, which is different kinds of activation, what information they have, and then move to convolution neural networks before we, at least my lectures are over, and then we potentially take over some of these topics in the main school. Anyway, Shanmai and partly me will cover graph neural networks, so we can see how these concepts change. So I will first quickly cover linear regression that all of you are familiar with. Then just very quickly highlight that linear regression can also handle nonlinear data by, it's effectively the concept of the kernel, but that is called a locally weighted regression. Then come to the important topic of the logistic regression, which kind of laid the groundwork historically, but also otherwise, of a of the concept of a neuron activation. All of that came really from a logistic regression, and that concept was taken to its logical conclusion by what we call these vanilla fully connected deep neural networks, but I'm calling that deep learning with MLPs, multi-layer perceptrons, where today we want to see the mathematics of the activation, forward propagation, backward propagation. Okay, so let's dive right into it. So I have a n-dimensional input feature vector. So the problem statement of the linear regression is I take theta transpose x, okay, where these thetas are my model parameters. In general, if I have n-dimensional input features, this will have n plus 1 dimensions, right? If you break it up, this will be theta 0 plus theta 1 x1 plus theta 2 x2 dot 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 plus theta n xn. Okay? And then what is your learning goal? Learning goal in a linear regression, your learning goal is you minimize half of so I have already used n. So if I have m data points, I equal to 1 to m, which is the data size. Okay, data size. I want to minimize h theta xi minus yi, that's your label, whole square. Clear? So what is the simplest example of a linear regression that you have come across? Does this form sound familiar? Where do you, in what exercise that you do, I believe even in college, you have this kind of a problem? Least square fits, right? That's the simplest example of a linear regression. Anyway, so then what are the things that sound a little not nice to you is after all this game of loss function that we discussed, I directly use this h theta minus yi square. I did it purposely and we will come to that. So then how do I solve such a problem? So I've completely specified the problem for you, right? You have m data points. Each data point has n input features. So you want to fit on it. So then if I give you an unknown data point, you have to predict what the y value of that point would be. So I can represent my predictor as theta transpose x. Okay, there's a mistake I did here. Well, no, it's correct. The theta 0 is the bias term. No, it's fine. So it just takes a linear combination of the parameters and the input features, and you are deriving these thetas by minimizing this learning goal. Okay, so then what would you do? So you would choose some initial values of theta, use gradient descent to update thetas. Then you want a stopping condition. So sorry. So I can call this 1, I can call this 2, I can call this 3. Repeat 1 and 2 until stopping condition met. Okay. So basically what I'm saying is I have a theta j. So my theta j will become theta j minus alpha del theta j loss function, which is a function of theta, and your theta j plus 1, that is the so this remember, this is a n-dimensional equation, right? N dim equation, because n plus 1 dim equation, because you have n plus 1 thetas, and j is the jth iteration. So your theta in your j plus 1th step will be theta in your jth step minus, you do the math, it will become alpha h theta x minus y times xj. Okay, so with this, algorithmically you can simply write down your own code to solve this problem. This alpha is nothing but the learning rate, right? So remember the other day someone had asked this question on gradient descent. So that learning rate, what should my step size be? So we had discussed this, that you start with some step size, you descend where this parabola represents some form of the loss function as a function of the various parameters. There will be a time you might miss the minimum and you might climb up. So then you retrace the steps, reduce your learning rate. So all those things you can apply here. Okay, so that completely defines the linear regression problem. Are there any questions? No. So there comes a question: uh, can we use this for non-linear data? And the answer is absolutely yes. In the simplest case, you do a variable transformation, right? We are used to doing log plots, right? When there's a log relationship, if I take a log of a parameter, it can becomes a straight line where you just have to read your x as log x. So in a simple way, you can just do a variable transformation, but that's like a global thing. But a global thing can always be broken down into a sum of local things. Locally, you can weight your points based on whatever parameter that you see, right? You can do a local variable transformation as well, because the entire loss is ultimately a sum over the full data set. So you have a certain feature vector space. Your xi's to xn, they span a certain phase space. So you can always sort of transform chunks of this phase space into whatever form you want. So bottom line is, yes, by being sufficiently innovative, when you know your own data set that you're dealing with, you can use this to do a simple. You can use this to work with nonlinear data. Okay. So now comes your assignment, or what should I call it? Say question question one for say 26/5/25 lecture. Okay. I mean, exactly this I will send you writing out. So the question for me is, why minimize a least square? Okay. So I just wrote this down, right? Learning goal that. And it was asked, I think, why do this? What is the justification for this? So uh, I will try to make this a little more concrete. Okay. So I will just formulate the problem for you. You will have to do the derivation, and maybe Riteshda can set a time by which you have to hand it back in. It cannot be handed back in 1 week later for sure, but whether it's 2 days or 3 days, I think maybe Riteshda can take a call. Okay. So yi, that is the prediction the model makes, is theta transpose xi, right? That's the prediction. Sorry, wrong. Yi is your true label, correct? Every point has a xi, which is your feature vector, and a true label attached to it. In a least square fit, for every x, you have a y attached to it. That's your y. This is your model, theta transpose xi, that you have trained. But no model is perfect. So every step you will be making some mistake. I will not predict yi perfectly. I will have some error. Okay, I'm calling this the error. So now I make another assumption that, but that's a reasonable assumption, that assuming the model I've trained has no bias, and if there is a bias, it will show up in when you train. So suppose this error is distributed as a standard normal distribution. Mean zero, not a standard normal. This is not standard. Standard normal has, I think, standard deviation of 1, but this has sigma. So Gaussian with mean 0. Okay. So then my probability of this is 1 over square root 2 pi sigma exponential of minus sigma I. Just bring this, or maybe up there. Yeah. Sigma I whole square by 2 sigma square. Okay. Then another assumption. So I have these for the n points, right? This is for 1 point. So assume these sigma i's are IID. IID means identically individually distributed. That there is no correlation between them. They are independent of each other, identically independently distributed, and independently they follow this Gaussian distribution. Okay. So then I can make this more concrete. Yi, probability yi given xi, but semicolon theta, right? Because this probability distribution function depends on the model. That will be equal to 1 over square root 2 pi times sigma. Now I can write it out as exponential minus yi minus theta transpose xi square. This is the most critical step. So please tell me whether it's clear to you. One, this is an assignment problem for you instead of a quiz. This is an assignment problem. You have to hand it in a few days, maybe 3 days max. I think that's a reasonable time frame to give, where we are trying to ask ourselves, why is it sufficient to minimize a least square in a linear regression problem? So then we are formulating the problem as, I know what the true label is, I know what I predict. The difference between the two is your error. I make an assumption that these are distributed like a Gaussian, that I get to predict them but with some error. And then I make another assumption that they are IID, identically independently distributed or independently identically distributed. Then the probability distribution function to get a given yi for certain xi's given thetas is distributed like this. Okay. So then what no one can object to is, now I say y vector. This is over m points, right? To get the full data set given x semicolon theta is the product over m points of Are we on the same page? We are doing maximum likelihood minimization. Okay. If I know probability to get a yi given xi theta, then the likelihood to get thetas will be by minimizing the minus 2 NLL of the probabilities for the M points, right? So this first P is this first P that I wrote here. I don't know how to point, but you can see the first P that I wrote in the likelihood equation is to get the full data set. That can be broken down into the product of these points. So now prove that a minus 2 NLL extremization is identical to minimize, did I write correctly? Minimize, yes, minimize half I equal to 1 to m yi minus theta t xi. Okay, so first maybe take 30 seconds or 15 seconds to just maybe I'll just unzoom it so you can see more of it. Okay, I think you can see all of it in one screen now. So the question here, no, here, yeah, okay. So one of you had raised, I don't know in what context, one of you had raised, why are we doing this least square? So what you cannot argue is in order to minimize something to do a fit, it is sufficient to do a maximum likelihood extremization. That has no assumptions, right? So what I'm trying to sort of set up the problem with some assumptions, of course, then you can argue if those assumptions are not valid, what will happen? Those are valid questions. But doing a minus 2 NLL extremization is the same as minimizing this chi-square quantity. And this brings a very important lesson. The important lesson is when I have sufficient statistics, there is no difference between a chi-square minimization and a likelihood. So maybe I can add that, okay? And motivate why chi-square minimize. Okay, I don't know why this is not working. Yeah, this. Okay, then maybe let's make it a little bigger. No, 50%. Why chi-square minimize? Motivate by chi-square minimization is identical to minus 2 NLL when M is large. Okay, so is the question clear to all of you? Then we can move to the next problem. I don't know, is this too easy or clear? Just I need some feedback. If it's too easy, then I would jump to something at the next complexity level. Okay, are you still connected?
Yes, sir.
Okay.
Yes, sir.
Okay, but the question is clear and you have to hand it in. That is also clear, right?
Yes, sir.
Okay, very good. Okay, so now we move to the next problem, and perhaps that's where we will have to stop. What do I do? Okay, I can export this as PDF and send it. I promised to send it a little earlier, but I will send it right after this class. And how do I do a new one? New. Uh, Maybe I can do it here. Sorry. Uh, okay. Okay. Uh, I want to discuss with you binary classification. Okay, what is binary classification? What you predict is an element of either 0 or 1, right? You can call it SB, you can call it plus minus, but ultimately it can take one of two outputs. Can I do a linear regression to do a binary classification? I want a few answers. So what do we learn? We have learned that a regression, the output it gives is continuous. It's not discrete. A regression cannot give a discrete output. But in your BDT example, we saw the case, right? You can always represent your continuous output in tiny chunks, and in those tiny chunks, you can take the average. I believe the slides were also shared with you. So you saw that. So can you tell me what are the drawbacks of doing binary classification with a regression? With a linear regression, sorry. None? I don't know. I know many of you in this list know all this. You're keeping quiet because you know the answer and you don't want to show, or what? Anyway, fine. Let's just do it. So, what effectively is. So, you have a situation that's something like this, right? That I'm drawing y. I'm just drawing y. I'm not saying when y is that. But effectively, in your data set, for certain set of values of your input features, y takes one number, and then even if one input feature changes, it abruptly changes form to another one. So say this is 0, that is 1. If I'm using a linear regression, yes, all those things of I said locally weighted, blah, all those are valid. But if I'm taking a linear regression, I can't do an abrupt turn on, right? I can make the slope as steep as I want, but no matter what I get, you see that around the midpoint here, these many values I'll be misclassifying, as will I be misclassifying these many values. I can always use a linear regression to say to do classification by saying when my y reaches that value, predict this. When my y reaches the other value, predict that. But as you see here, I cannot do an infinitely sharp turn on. That would lead to overfitting, right? So it is really with this that we will come to the concept of activation. And that was for the first time implemented in logistic regression, and then we will see what solutions we get. Okay, so in logistic regression we need an h theta x, which is an element of 0, 1. Okay, so we want to sort of by definition solve a problem like this that a linear regression would find it hard to solve, where that ultimately I can have whatever slope, whatever combination of slopes I want, but my output will be linear with respect to the input features. It cannot have an abrupt change of form. But to have a good binary classifier, I need a step function, right? So those of you who know activation now will automatically, or unless you already knew it, that's fine. But now you know the direction in which we are heading. That why do we need activation in relatively advanced model? So then the problem statement of logistic regression becomes I need an h theta x. Earlier h theta x was what in linear regression? Just theta transpose x. But just theta transpose x has that problem. So now I want h theta x equal to, so it cannot just be theta transpose x, right? I need some function that will solve for me that problem that I specified. In logistic regression, we use the famous sigmoid function where gz is equal to 1 by 1 plus e to the power minus z, right? Where if you draw it, so what is this? So is this familiar to many of you, this concept of this sigmoid function?
Yes.
Okay, at least to some of you. So what values are this function bounded by? Anyone please speak up. What values are these functions bounded by? Very good.
0 and 1, sir.
Yeah, perfect. And it has a sharp turn on. So if this is 0.5, this is 1, that's 0. Right? This is what that function looks like. So is it quite clear to you that just by choosing this activation, which will have many side benefits, instead of having to decide based on this straight line, we now effectively have a step function like so. Otherwise, I would have had to depend on some kind of a straight line, right, in the linear regression case. Clear? So what are we doing in a logistic regression? Input features same. They are being inputted into, so let's draw it this way. So, okay. Effectively, let me just say, I mean, we already kind of have a concept of a neuron. Why? For one data point, I have xn, x1 to xn, right? If I call this a neuron, represented this way, I'm changing just one small notification and I will come to you. And we will follow this through in the next time. So I'll just show you. So if you look at h theta x, what is it taking in? It is taking in x's. It is multiplying the x's by a set of weights, right? Which we had represented as, sorry, I changed the thing. So if you go back to your linear regression notes, I had represented them as theta 0 plus theta 1 x1, theta 2 x2, blah, 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 right? So then if I call theta 0 b and each of the w's as theta 1, theta 2, so I have here when the one data set enters this round object, which I want to call a neuron, it gets multiplied by weights and biases, or theta 1 x1 plus dot 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 theta n xn plus a theta 0. Not just that, but it gets hit with an activation component that I'm calling sigma. So this I can call sigma, which is your sigmoid activation, theta t x. Okay, and I can have more of that. So why is it neuron and all? There's some biological reason. We'll come later when we do DNA. But at the core of the logistic regression is this sigma. Otherwise, it would have just remained the linear regression. Okay. So now I will gradually motivate your second assignment problem, but let's first do it systematically. Why is it not going to the next page? Oh, it's quite late already. Okay, maybe I can write here. Okay. Okay. Hello.
Yes, sir. Audible now.
Yes, where did I get muted? Okay. So we are trying to let's say now. So we set out the problem of what the operation is, but what do we try to minimize in a logistic regression problem? So probability to get one class, if I call that h theta x, necessarily probability to get the other class will have to be 1 minus h theta x, right? So then you kind of have a binomial kind of a probability distribution scenario where the probability to get one class is not 50%, right? So in that situation, probability to have y given x theta. So now I'm kind of combining the two scenarios. This, you can convince yourself, is h theta x to the power y 1 minus h theta x to the power 1 minus y, right? So I have two scenarios. In this paradigm, To get one class, if that is h theta x, to get the other class has to be 1 minus h theta x. So you have a binomial kind of a distribution. It's just that the probability to get right or wrong is not is not 50%, but a number. So you can write it out that way. So then what do we do? Same likelihood method. L theta equal to P y I xi given theta. Okay. So then I have to multiply this probability distribution function over m data points, right? So the notation we are following is that I have n input features. So xi goes from 1 to n, but I have m data points, right? So when you have a likelihood, you have to multiply the probabilities over each data point. So that becomes Pyi given xi colon theta. So now you substitute the expression that we wrote. You substitute this expression back over there. So that becomes pi I equal to 1 to m h theta xi to the power yi 1 minus h theta xi to the power 1 minus yi. Okay, so then what does the problem becomes? You have let's say L theta, you can now take a log of capital L theta, log likelihood. You can do negative log likelihood if you want. And then what's the advantage? So, okay, quickly. In a log likelihood, in a likelihood, why do we take a log? What's the benefit of taking a log? The product becomes a sum. Here I have a product, right? The product becomes harder to bookkeep. So the moment I take a product here, so this becomes a sum of I equal to 1 to m yi log h theta xi. Clear? The yi in the power comes down, plus 1 minus yi log 1 minus h theta xi. Is it clear to everyone? Because this is a fundamental result that in a binary classification problem, maximal separation between two classes is obtained using a likelihood figure of merit by minimizing yi, that's a class, log h theta xi plus 1 minus yi log 1 minus h theta xi. Okay, this is also called your logistic loss. So can you see that I had listed this in one of, I think in the first class that I took, and someone had asked, where does this form come from? So this is where this form comes from, that if I simply want to do a likelihood fit to obtain parameters of a model that maximally separate between two classes using a likelihood minimization. Now, why a likelihood is good or not, you can follow your statistics lectures. But if you give me the leeway that to obtain a fit, the best thing to do, if it is a likelihood minimization, in the case of a logistic regression, the problem, just excuse me, I have to take an urgent call. Um, the problem reduces to minimizing this figure of merit. So this we call the logistic loss. Are there any questions? So this is quite a important result. So do you have any questions till this point?
So
No.
what exactly have you
I
written
don't know.
after FOM?
Sorry?
So what exactly have you written after likelihood?
After?
Likelihood.
Uh, you mean this thing?
No, sir, in the left side.
In a binary classification problem, maximal separation between two classes is obtained using a likelihood figure of merit, or FOM, sorry, figure of merit, by minimizing this, which is we call the logistic loss. Okay.
Yes.
Excuse me,
Any
sir.
other questions?
Excuse me, sir. Could you
Yes.
show where we start from? I lost connection in between. I mean, how do we arrive at this? So our first step will be to look at. Okay.
Okay.
Okay. Yeah, got it.
So your probability to predict something, say one class, is h theta x, right?
Yes.
So probability to predict the other one, to conserve probability, is 1 minus that.
Yes. Got it.
So then you have a binomial like probability distribution function. You follow that through.
Yes. Sir. Thanks.
Okay, shall we move on then?
Yes, sir.
Yeah, I don't know why I can't go to the next page. This iPad I'm using for the first time. Oh, no, this is not what I want. How do I go to a new page? Anyone has any idea? I'm using something called Freeform. Okay, maybe I'll take track. I'll do something. Title this one. No. Maybe here. I just rub this out. Okay. 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 So then let's completely specify the problem. So let's say, excuse me. Okay. So yeah. Flow chart for the logistic regression problem. Ouch, sorry. One. So remember I represented the h theta x was equal to an activation applied on a theta tx, and this theta tx I called it w0 plus w1 x1 plus dot 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 wn xn, right? And this I'm asking you to identify with a theta 0, and these are w1. So first I have to initialize w's and b's. Two, I have to find optimal w's and b's. Once I have done that, in the third step I can predict using this sigmoid activation wx plus b to do a prediction where this sigmoid is nothing but like a 1 plus e to the power minus z. So then the main challenge is how do we get this step? So like we said, the recipe we follow is we have a loss function which is nothing but the logistic loss, which is log y hat. This y hat is nothing but h theta x because I'm using different expressions. You have log y hat plus, let me just rub it out so it's clearer. Yeah. 1 minus y log 1 minus y hat. So be very clear that there's a difference between a y and a y hat. Y is your true label. Y hat is your prediction. Okay. A loss function should have both your prediction and your label, and it wants to bring them as close to each other as possible. So the loss that we use is this form, and you have to be careful which is y hat. So then what do? We do gradient descent as usual. So you can define your new w in your j plus 1th step as w in the jth step minus alpha del L del W, and B in the j plus 1th step as B in the jth step minus alpha del L del B. Okay. So once you know how to take derivatives, you have a well motivated loss function which should work. So the beauty of a logistic loss is because it has come out of a likelihood kind of an estimator, it should work for arbitrary classification problems, except where the assumptions of likelihood being the optimal estimator breaks down, which is very rare. Okay, so I hope the logistic loss problem is clear to you.
Yes.
Good. Ouch. So let's rub this stuff out. So now I want to do multi-classification with a logistic loss estimator. So let us do, I don't know why it's so small. How do we make it big? No, it's not working. Multi-classification. Okay. So I am going to follow a certain thing. So earlier, wait, where? Maybe here. Yeah, here. You see over here, where we said we have a model of a neuron over here. You were connecting your input features into one of these circles. You're doing a WX plus B and you're doing an activation. This neuron itself is telling you 0 or 1, right? When I do multi-classification, I might want 4 answers, 1, 2, 3, or 4. It can be various things. I'm not going into it. But what we have built so far is I connect my input features to a neuron, and that gives one of 2 answers, 0 or 1. Now I want to do multi-classification is I want more answers. So I want to change the model slightly so that each neuron gives 1, 2, 3, or 4, ideally exclusively. Okay? I think here, right, yes. Okay. So now I have x1s to xn's. Just as an aside, my data set I can represent as a square, right? I have n, I have output feature not counting. I have n, what do you call it? I have n input features. That's like one row. And I have m data points. So m rows of n columns, right? So now what I'm doing is one by one, suppose I want to do 3 classifications. Okay. So I want to put in the data set into each of these 3 nodes, and the output of each node I am representing by A1, 1. And you will see I'm introducing gradually the the notation for a deep neural network. That will be clearer when we get there. 1, A3, 1. Okay, so this notation is node or neuron. If you're not yet convinced that this is a neuron, why is it a neuron? You can call it a node if you want. Node? No. Yeah, you can call it a node. A1, A2, A3, 3 neurons, and the one in bracket represents a layer. And then the input data set, all of it is put into each of those neurons. And when they are put into it, what do? They get weighted and a bias added. Okay. So now let's say what is the output of each neuron, or sorry, what was I calling it? Output of each neuron in layer 1. So Y1, and the output I'm calling A1, 1 is nothing but activation of weights in layer 1 plus B1, 1. And I want to call the inner part of this as Z1, 1. Let me write it out, then I will explain more. Oh, it's almost 12. Ritejda, can I take 15 more minutes? Hello? Ritejda, are you connected? Okay, I will take 15 more minutes, okay?
Yeah, okay.
Yeah. Uh, y2 is equal to a21, which is equal to sigma w21 x plus b2 1. I will call this as z2. Likewise, this output I'm calling as y3, which is equal to a31, which is equal to summation w31 x plus b31, and this you can call as z of 3 1. Okay, please pay close attention to this notation, because literally this will be transported to the deep neural network case. So I have 3 neurons. The outputs of them are being represented by this A terminology, where there's a subscript and a superscript. The superscript refers to a layer. So if I, for whatever reason, had another layer of these, those would be A bracket 2. And then the subscript is as many of them as I have. Okay. So then the output of a neuron y hat 1 for the A11th neuron, that is the output, that is a activation times weight. So I have n weights per neuron, right? So W1 is actually a vector. W11 refers to the weights of the first neuron in the first layer. Likewise, the biases of the first neuron in the first layer. And this dot product Wx plus B I'm referring to as Z11. To get the output, I have to apply activation on it. Likewise for the others. Is this notation crystal clear? I assume it is. Okay. But then what should be my labels? When you did that Higgs to tau tau problem, you had SB, right? That you transform to 1, 0, that you transform to 1, 0, etc., etc. You can also have any other thing, but they have to be unique for the two classes. Okay. So here, what should the label of your training data be? So logic demands that you could give something like 1, 0, 0, 0, 1, 0, 0, 0, 1, right? But in this neuron formalism, sorry, I don't know why it happened. In this neuron formalism, you can even give 1, 1, 0, right? What's an example, right? I have a picture in which, I don't know, dog, cat, and a hen, maybe, right? 1, 0, 0 means there's dog, no cat, no hen. 0, 1, 0, cat, not. But suppose there's both a dog and a cat in a picture. Then I can give one, excuse me. Okay, so you can have 1, 1, 0. This formalism doesn't have any problem if you want to do that. But Now it's a question. So basically, so what am I saying is that we deal with label data, right? What the label should be is in your hand. If I know for sure this is signal and not background, I do BS. Here you're allowed to give 110, but what does that mean? That the output that your network gives can have, I have both a cat and a dog in an image, right? What if I want a unique outcome? Let's say I can have Higgs, my event can only be Higgs and no background, or my Higgs can be, it can be Higgs and QCD background, no Higgs QCD background, no Higgs electroweak background, something like that. What if my data has a unique outcome? How do I change it? Okay, the question is clear to you, right? That this formalism that I gave you, as long as the node activates after I train, you would train it based on gradient descent. As long as it minimizes, you have models of theta. If that node gets activated, it will predict 1. So it can predict 1, 1, 1, 0, 0, 0, and any combinations thereof. What if I want a unique outcome? What do I do? Anyone has any guesses? So that's where you have to change your output to what's called softmax. And with this, I will end for today. Let's see if I can find something. I don't know. Here. Okay. So I covered with logistic regression, you can do multi-classification, but if you use the sigmoid activation, it can do, okay, I don't know. I'm sorry, my pen is stuck now, it's back. Okay. Add a constraint for an unique outcome. Okay. So what you do here is I still have 3 nodes, right? I remove that sigmoid activation, and I normalize the output. I take something like this: exponential sum over k equal to 1 to 3. I have k classes, e to the power zk 1. Okay. Likewise, this will be e to the power z2 1 divided by that quantity, which is sum over k equal to 1 to 3 e to the power zk 1. And likewise, this will become e to the power z3 1 divided by the form I have been writing down. This is called a soft max multi-class. I haven't introduced network yet, but network. In this, you're constrained that the output will be unique. It will predict one of the 3 will have sort of the highest probability. Need not be a probability, the output will be a probability, but you are constraining the sum of the probabilities to be 1 by design. I repeat, I sort of slightly take back what I said, that it need not have a unique output. That is in your hand. But what it is doing is it's predicting the probability that the kth neuron has the kth output, with the constraint that the sum of the outputs of the network is 1. Okay, but now comes the question for you. So can you now immediately notice what the problem is? I cannot use in this derivation, we had the assumption of 2 classes, right? You recall, right? We did probability to predict 1 is h theta, probability to predict not 1 was 1 minus h theta. The probability distribution function was h theta to the power y, 1 minus h theta to the power 1 minus y, and then the derivation went through. Can this work for 3 classes? It cannot by definition. So your task is prove that in the soft max case, optimal loss function is sum over k equal to 1 to 3 minus yk log y hat k. Clear? So y hat k is defined like so: e to the power z1 divided by the sum of that. Z1 is itself W1 times X plus B, W2 plus X plus B. But prove that the optimal loss function for a softmax multi-classification is, the sign is not so important. So all this 1 minus doesn't come, yk log k, and this is what's really called the cross entropy loss. Okay, so this was assignment 2. Okay, I will write it out, of course, and give it. So my final question is now, so this was binary classification. What if regression? That energy problem, that electron energy problem. Suppose I wanted to do that electron energy problem. I cannot use a sigmoid, right? Sigmoid will give one of 2 classes. So that is no good. What do I do? Very simple. Change activation. 1, activation 2, ReLU, for instance. There are many other options that we will discuss. So what is ReLU? Everywhere to the left it's 0, and then everywhere to the right it's a straight line. You can change the slope of the straight line, all that is fine. But the moment you do ReLU, you're not bound to predict discrete values. You have the ability to predict continuous values, and from your cross entropy loss or your logistic loss, you change your loss to mean absolute error or MSE or semi-parametric if you are interested in it. Okay. So I think this is a good place to stop today, where I think we have covered quite a bit of content on one, how to make a regression semi-parametric, how the traditional or the popular minimization metrics like chi-square or this logistic loss come naturally from a maximum log likelihood picture. and how in a logistic regression, the concept of activation is introduced to the concept of activation is introduced to be able to do a binary classification from a regular linear regression problem. And gradually how like a layer of a neural network is forming from these activations. You can also do multi-classification, where if you want a unique output, you need to introduce softmax, where you normalize the probabilities. And then to do multi-classification, your question 2 is the form of the loss changes, but it's not limited to do classification. You can also do regression. All you do is change your activation, change your loss. Okay. I think I would like to stop here today, and we continue with the deep network and the CNN in the next class. Okay, any questions? Any questions? I think I will stop here today. So if you have questions, I can address them. And you have 2 assignment questions to hand in by Thursday, let's say. Okay, if there are no questions, sorry, I might have taken. No, I will send an email. I'll after lunch, I'll send an email with the 2 questions as well. But, yeah. Okay, Riteshda, I think I overshot a little bit, but I think this is a good place to stop before the next class. And I will send the PDFs of all the notes. Okay, so I think I'm going to disconnect here. So don't worry that the assignments are not there, but I will just write them out and send them in. Okay, thanks a lot, guys. So we'll see you on Wednesday. Okay, bye-bye.
Thank you, sir.
You can drop a mail to the common thread and send it wherever.